Hello guys, welcome to my video. So today I'm going to be solving the May-June 2022 question paper 1-2 for physics, and the question paper is 1 hour 15 minutes long. So I'm going to be going through some of the questions that were asked on this paper so that you can be able to understand how some of these questions can be worked out. So I really hope that you enjoy my content. If you have anything that you would like me to improve on, I would highly recommend if you have anything that you'd like me to improve on, I'd highly recommend that you mention in the comment section. And if you have a specific paper one, right, that you want me to work on, I'd highly recommend that you put the paper down with the code. You know what exactly is the paper and what variant it is, so that I can be able to work on it, right? So I really hope you enjoy the content. Please comment, like, share, and subscribe. And yeah, so let's begin. The first question, we've been asked which estimate is reasonable, okay? Right, so for the first estimate, we've been given 1 times 10 to the power of negative 3 for the mass of the grain of sand. So the mass of grain of a sand is very, very small, but 0.0001562 grams, right? So it's very, very small. It's not even equal to 1 times 10 to the power of negative 3, right? So how are you supposed to know this? I don't quite know, but the thing with estimates is you just have to know a lot of things. But some of these come from, trial and error, right? Some of these answers will actually make much more sense than others, right? For example, with B, the radius of a normal tennis ball, as you can see over there, is about 6.58, right? About 6.58 centimeters approximately, right? So if I want to find the volume of that, it would be, since it's a sphere, 4/3 pi r cubed, which would be 4/3 multiplied by pi, multiplied by the radius 6.58, times 10 to the power of negative 2 divided by 2 cubed. That gives me about 4.5 times 10 to the power of negative 3, right? But here they essentially gave me times 10 to the power of negative 2, so it can't be B, it can't be A. The work done to lift an apple from its height to head height. So consider this person, okay, and wants to lift an apple from his waist up until his head, right? So we can basically I can assume that's about 60 centimeters, right? So that's an overestimation, but let's just assume that it's 60 centimeters, right? The worst case scenario, right? So the mass of an apple is basically, so if I want to find the GPE, it's basically mgh, right? So the mass of an apple is 300 divided by 1000 times 9.81 times the height 0.6. It's about going to give me, about 1.7 times 10 to the power of 0 joules, right? Pretty much close to, to C, because it's 1 times 10 to the power of 0, right? And the power of a light bulb, if you've looked at a light bulb itself, right, there's about 60 watts, right? So this is way an overestimation, right? So the correct answer is C. So if you're going to use elimination, your answer would have been C. So I highly recommend that you use it so that you can be able to see which answer is correct, okay? Moving to question number 2, we've been asked which symbol is the SI base units for temperature. So the SI base units for temperature is the Kelvin. As you can see on the right, I've put all of the SI base units that you'll be asked to know for AS. Remember, the candela for light intensity and the other one are not really quite the amount of substance. They're very important, but they're very not that much examinable. But the first ones, they're very much examinable. So I recommend that you know them, right? Question 3. We statement about systematic errors is not correct, right? So the most keyword is not, okay? A systematic error can be caused by using a incorrectly calibrated instrument. That's true. So it's not correct, right? One particular type of systematic error can affect all the measurements by the same amount. That is correct. So what happens to systematic errors is if you have a systematic error, and this is your original graph, right? This is your original graph over here. Okay, a systematic error is going to cause a deviation of the graph, right, above and below. So basically, this is an overstatement, right? You're overstating, but here you're understating, right? Understating, and here this is the actual. Okay, so a systematic error, all the errors can either be above or below, but all of them has to be uniform, right? So they have to differ by the same amount. The effect of a systematic error can be reduced by repeating and averaging the measurements. This is not correct. You don't necessarily reduce the systematic error by repeating and average the measurements. So that is not correct. Zero error is a type of systematic error. That is correct. A zero error is basically if your instrument is not starting at zero, it shows that that instrument has a zero error. So that is not correct. Okay. Moving to question number 4. An object is moving with an initial velocity of 4 meters to the right. The velocity of the object changes so that its final velocity is 3 meters per second downwards, as shown like that. And want to find the change in velocity. So the most important keyword to notice here, the question is saying the change in velocity. What is the change in velocity? Well, basically, the change in velocity, okay, the change in velocity is basically the final velocity v minus the initial velocity, right? But in terms of vectors, usually v plus negative u, right? So if I go back to my initial one, it's going to be v, my change in velocity, change, right? Final velocity minus initial, right? V plus negative u, right? So the v is correct because the v is acting down, okay? But it's going to be plus, okay? The u, which is acting in that direction, so for it to be negative, it needs to be acting in that direction, right? So how do I find the arrow which represents the change in the velocity? Well, that's pretty simple. How then do we find the velocity? Well, again, remember, I always say this, whenever you have these two particular systems, you can just connect your vectors, right? So if you connect your vectors at a common point, right? So if you're going to connect them at a common point, right, that's going to be like that. One is going that direction, and we're also going to connect that over here, and one is going in that direction, right? The resultant force should be acting somewhere in the middle, right? So this should be the resultant of these two vectors, right? So this should be the value of your change in the velocity, right? So the change in velocity, the answer is going to be B, right? Very important, right? So the keyword here, which was quite tricky, was the change in velocity. You're not going to add this unless you have a negative u, negative initial, okay? Very important. A car travels anti-clockwise along a horizontal circular road of radius 12 meters. As shown, the car takes a time of 4.0 seconds to move from position P to position Q. What is the magnitude of the average velocity of the car from P to Q? Okay, so basically, average velocity, okay, so average velocity is actually going to be the displacement, right? The total displacement, okay, divided by the total time taken, okay, divided by the total time that is taken, right? So what is displacement? The shortest distance between 2 points. So considering point P and point Q, what is the short distance? I join these 2 points. This is 12 meters. That is also 12 meters, okay? So basically, this is the hypotenuse, right? So the hypotenuse R is the square root of 12 squared plus 12 squared, right? So the shortest distance is P and Q, right? If you're going to find this arc, basically, if you're going to find this arc, you're finding the distance. You're not finding the displacement, right? So the value of R, which is the displacement, is basically going to be the square root of 12 squared plus 12 squared, right? So it's going to be 12 root of 2. The total time taken is 4.0. That's going to give you an answer of 3 to 2, about 4.2 2 seconds, which is A, right? So very important, right? Just be thinking about this. Displacement is the shortest distance between 2 points, right? So paper 1 is basically about testing. Do you really understand what displacement is? Do you really understand what distance is, right? Very important. I'll move on to question number 6. I'm given a water that is in a deep well, 78 meters below the top of a well, right? So let's draw it. So this is our water well, okay? So basically, that is our water well, okay? So this is our water. Let's put it over there, right? Okay, and this is our water, right? So it's our water down here, okay? Right. So we've been told that a person at top of the well drops a heavy stone down the well, okay? So we have a person over here, okay? And the person is going to drop a well, right? A stone down in the well, right? And, you know, the well is 78 meters below the top, right? So it's like that, right? That, you know, it's about 78 meters, right? So a person is going to drop it, and the speed of sound in air is 330. So we're just going to keep this around. The speed of sound in air is 330. And one find the time interval between the person dropping the stone and hearing it hit the water. Get this. The stone has to travel, okay? So the stone has to travel down the well. Okay, so the stone has to travel down the well, down the well, down the well, down the well, and it's going to hit the water. As soon as it hits the water, it's going to send a sound wave that's going to go back, okay, up, right? And this person is going to hear the sound. Okay, so the stone is going to fall, and the stone is going to hit the water, and the sound wave is going to travel up. Okay, so how do I find the time taken for the stone to hit the water, and then the time taken for the sound to reach the person? So basically, my total time, okay, my total time consists of two things, right? So my total time, right, consists of two things, right? Basically, the first one is time, right? Time taken by stone, okay, by stone to reach the water, okay, basically, plus, right, plus, then I'm going to add the time taken by sound, okay, sound to reach the person, right? So basically, the stone is going to take a second time to reach the water, and the sound is going to also take a certain time to reach the person. Two different motions, right? So the time taken for the stone to reach, we know that h, okay, we know that h is equivalent to v naught t, okay, plus half gt squared, right? So this is 78. This initially is going to be 0 at the beginning, right? This will be half times 9.81 times the time squared, right? So the value of time will be 78 multiplied by 2 divided by 9.81, the square root of that. That's going to give you a total time of approximately, I think, 3.98, okay? So approximately 3.98, 72 seconds, right? So this is the time taken by the stone to reach the water, right? But we still have to add the time that the sound is going to take to reach the person, right? But we know that time is equivalent to the distance divided by the speed, right? But the distance is actually 78 divided by 330. That's going to give you 0.23. Okay, so the total time, therefore, is going to be equivalent to, okay, the total time is going to be equivalent to 3.9872 plus 0.23, right? Plus 0.23. And that's going to give you a total of approximately 4.22 seconds, right? 4.22 seconds. Basically, the answer is D. So get this, guys. The stone is going to take in time to hit the floor. This was really complicated. But the stone is going to take in time to hit the water. But the sound is also going to take a certain time to reach the person, right? So the sound is going to take a very short time, 0.2223, but the stone is going to take a longer time to hit the water. So the total of these two is basically the time interval between the person dropping the stone and the person hearing it hit the water. This was very complicated, but I hope it made sense. If there's anything unclear, please put in the comment section, and I'll be able to address anything that is unclear. Okay. Question 7. We tell me it's not a requirement of a pair of forces that obey Newton's third law. I always say this, right? MOSA, okay? MOSA, right? M stands for the forces need to have the same magnitude, okay? Very important, right? The forces need to be opposite in direction, right? Opposite in direction. Very important. The forces need to be of the same type. If they're gravitational forces, they both have to be gravitational forces. The third one, the forces have to act on different bodies, right? Act on different bodies. So, do they act in opposite directions? They do. It is a requirement. Do they act on different objects? It is a requirement. Are they of equal magnitude? It is a requirement. Do they act on objects in contact? Is that MOSA? It's not. So that is not a requirement. So the answer is C. The question says is not a requirement. Okay. So get this. For Newton's third law, they need to be same magnitude, opposite in direction, same type, act on different bodies, right? And if they don't obey those laws, they're not a Newton's third law pair. Very important, right? Question 6. A child of mass 20 kgs, okay, so a child of mass 20 kgs stands on the rough surface of a sledge of mass 40 kgs, right? So the sledge can slide on the horizontal frictional surface. Okay, so if given a child of mass 20 kgs that stands on the rough floor, okay, so the surface is rough, of a sledge of mass 40 kgs, right? So the sledge can slide on horizontal, but the surface is now frictionless, right? So very important for us to take note of those key points, right? One end of a rope is attached to the sledge, okay, so this end is attached to the sledge. The rope passes around the fixed frictionless pole, and the other end of the rope is held by the child, okay? So the child is basically pulling the rope. The rope is horizontal. The child pulls the rope with a horizontal force of 12 newtons. This causes the child and the sledge to move with equal acceleration towards the pole. So the child is basically, so if you look at the child is pulling the rope backwards, right, with about 12 newtons, right? But this is going to cause a tension, right? So it's going to cause a tension forward here of also 12 newtons, right? We know that tensions always act in the same direction. It's the same rope. So if that's going to take the tension, the rope below is also going to have a tension of 12 newtons, right? So at least we agree that, if it's going to exert a force of 12 newtons, the child to pull the sledge, the rope is also going to exert a 12 newtons moving forward, okay? So since the rope is horizontal, the child pulls on the rope with a horizontal force of 12 newtons, okay? So what is the frictional force between the child and the sledge, right? So what are we going to do here? We have to consider two things, right? We can consider the child alone, right? So the child is considered as a separate system. So let's do this. So the first system, we're going to consider the child alone, right? Okay, so if we're going to take the child, right? Okay, let's draw a child. Right, the child is going to have a frictional force, right? So the child is trying to move forward. So the child is holding onto a rope, okay? So this is the rope that the child is going to hold onto, and the rope is going to have a tension of 12 newtons, okay? So the child is going to push the rope forward with 12 newtons. The rope is going to try, the sledge is going to try to create, a frictional force backwards, right? So if the child tries to move forward, it's going to create a frictional force. The frictional force is going to be acting backwards, right? So this is the force of friction, right? That's going to be acting backwards, right? The child is moving 12 newtons. The force of friction is acting backwards with also that same force of what? Of 12 newtons, okay? So very important for you to be thinking of that. But Newton's third law then says that the resultant force, okay? So from Newton's second law, rather, it says that resultant force is the mass multiplied by the acceleration. So the resultant force is 12 minus the frictional force should be equivalent to the mass of the child is 20, okay? Multiplied by the acceleration. So this is my equation 1. So considering the child is going to push forward with a force of 12 newtons, and the frictional force is going to act backwards with a force F, right? So this is the first scenario for the child. The second scenario is for the sledge, right? So we're also going to consider for the sledge as we've considered for the child, right? So basically, let's look at the sledge as an independent system that is over there, right? So the sledge is connected to a rope, right? So the rope is also here, right? So the sledge is going to, again, experience a force going forward of 12 newtons, but there's also going to be a friction. But this time, the friction is going to be forward, okay? This is going to be our frictional force. Okay, why is this forward? Get this. As the child is about to move forward, right? As this child is about to move forward, okay? The frictional force is going to move backwards, okay? Because as the child tries to move forward, right, the frictional force is going to push the lorry backwards, right? But if you get this, friction is going to force the lorry to move forward, right? The sledge to move backwards. But as the sledge tries to move back, okay, as the sledge is trying to move back, there's a force, a tensional force that's pulling the sledge forward, right? So the sledge is trying to move back, right? Trying to move back because the frictional force is causing it to move back, but there's a force that's usually causing it to move forward, right? So initially, so for instantaneous, instantaneous moment, the child, okay, the sledge is sort of like going to move back, but it's going to, exert a frictional force forward, right? Because since it's going to try to move back, right, it's going to encounter a frictional force, right, that's also going to be acting in the forward direction, right? So As the child exerts the frictional force backwards, that's going to push the sledge backwards. But the sledge is also going to exert a frictional force forward in that direction, because there's also a tension causing it to move in that direction, right? So it's going to sort of oppose. So those two frictions are going to cancel out. Hence, the child will not move. As the child is trying to move forward, there's a tension, a frictional force pulling her back. And as the child is pulling back, the sledge is also trying to push itself also backwards, but it's also being forced forward. So the true frictional forces will cancel out, giving a resultant of 0 for the frictional forces, right? But we can still consider them. So these two things are going to be acting in the same direction, right? So the 12 newtons, okay, plus the frictional force should be equivalent to the mass of the sledge, which is 40, okay, multiplied by the acceleration, okay? So once we have these two equations, right, equation 1 and equation 2, we just go them and we solve, okay, simultaneously. Okay, let's do this. So how do we do this, right? We know that F, right, from that equation, F is equivalent to 12 minus 20A. Okay, so F, we substitute it in this equation. So this value of F, okay, we substitute it over here in that equation. So basically it's going to be 12, okay? So it's going to be 12 plus 12 minus 20A, right? It's going to be equivalent to 40, okay, multiplied by A, right? So that's going to be 24 is equivalent to 40A multiplied by 20A. So 24 is going to be equivalent to 60A. Okay, so the value of acceleration is going to be 24, okay, 24 divided by 60, that's going to be 0.4 meters per second, okay? But if you have that acceleration, the value of F essentially going to be 12 minus 20 times 0.4. And the value of F is going to be 12, okay, subtract 0.4 times 20 is going to give you a value of 4.0 newtons, and the answer is A. Okay, so this was a pretty complicated paper. I mean, the A was actually 24, so it was quite a complicated paper. And there were a lot of concepts that you really had to apply. But basically, you had to know that as the child moves forward, okay, frictional force is going to act backwards, right? But if the sledge tries to move backwards, it's going to have force causing it to move forward. Okay, so it's going to have a frictional force forward, and the frictional force and the tension will all be in the same direction, and they will prevent it from moving back because it's counteracting, the friction and friction are counteracting each other, and the tension is causing the child to move forward, right? It's very complicated, but I really hope it made sense so that you can be able to, answer such similar questions, right? Move on to question number 9. We've been given a stone, okay, a stone and a foam rubber, which are identical spheres of equal volume, okay? They're released at rest at time t is equal to 0, and they fall vertically through air. Both reach terminal velocity, which graph represents the variation of the time speed of the stone and of the rubber ball. Okay, so very important. I'm going to just explain one thing briefly. Basically, they have the same volume, right? So if this is A and that is B, okay, they have the same volume. Okay, if this is A, this is B, they have the same volume. But since one is made up of stone and the other is made of foam rubber, the masses are going to be different. This might have a mass of M, that might have a mass of 2M. So get this, the weight is going to act downwards, right? And the weight here is also going to act downwards. But you can agree that the weight for B is going to be greater than the weight for A. But for upthrust to happen, right? But for terminal velocity to happen, the weight, okay, should be equal to the air resistance, right? Should be equal to the air resistance. In other words, it should be equal to the drag force, right? The weight should be equal to the drag force. But if the weight is so greater for ball B, which is the stone, if the stone actually has a greater weight than the weight of the foam rubber, what does it mean? It means that the air resistance, right, for equilibrium to be reached, for terminal velocity to be reached, the air resistance of the stone then has to be greater than the air resistance of the foam rubber, okay, than the air resistance of the rubber, right? Very important, right? So as the weight of the stone is greater than the weight of the rubber, the air resistance of the stone will also be greater than the air resistance of the rubber, okay? But if the air resistance is greater, we know that the force is related to the velocity, right? A greater air resistance indicates also a greater force. So the stone is going to have a higher terminal velocity, okay, a higher terminal velocity, and the foam rubber is going to have a lower terminal velocity. So the foam rubber is going to have a lower terminal velocity. Okay, so the answer is going to be B. Stone with a higher velocity, the rubber with a slightly lower terminal velocity. Why? Because its weight is greater. If the weight is greater, the air resistance is also greater. If the air resistance is greater, it means that the force, the velocity also has to be greater, because velocity increases such that the so that the air resistance can be able to counteract that weight. Very important. Question 10. When we're given two bows X and Y moving towards each other with speeds 5 meters per second and 10, right? So they're basically moving in opposite directions, right? So we're going to apply what we call the relative speeds equation, right? So we know that the relative, speed of approach, relative speed of approach should be equal to the relative speed of separation, right? Very important. Okay, so how do you find the relative speed of separation? The golden rule, whenever we talk of relative speeds, if they move in opposite direction, right? If they move in opposite direction, what do? You add the speeds together. The second golden rule, if they move in the same direction, what do? You subtract, you subtract their velocities, right? So are they moving in the opposite direction? Yes. What do? We add 5 plus 15 should be equal to. The other one moves to the right with what? With 7. So the other one should move to the what? To the left. Okay? Because perfectly elastic means they do not stick. Okay? So 7 plus V. So 20. Okay? 20 will be equivalent to 7 plus V. Therefore, V will be equivalent to 13 meters per second. But to the left, 13 meters per second to the left. Okay? Very important. Okay, move on to question number 11, which two forces form a couple. So basically a couple is a pair of equal forces, right? Equal in magnitude, opposite in direction, and separated by a distance r. That's basically a couple, right? So a couple, they have to be in the same direction. Okay, very important, same direction. Number 2, they have to be equal in magnitude, okay? Equal in magnitude. And then number 3, they have to be separated, separated by a distance r, by a distance r. So are they in the same direction? No, they're in opposite directions rather. So they should be in opposite directions, right? Like here, opposite directions. So are they in the same direction? That's wrong. Perpendicular to each other? They're not perpendicular to each other. They're actually a bit parallel, right? Same magnitude, that's true, right? So the answer is C. Pass through the same point, they do not pass through the same point. So the answer is C. Question 12. So the other end of the road is supported by wire. So the road is horizontal and it's in equilibrium, which arrow shows the direction of the force on the road from the hinge, right? Very important. So get this, guys, right? So if you look at this, there's going to be a tensional force in this wire, right? So if we zoom in, there's going to be a force of tension, right? If we're going to resolve this force, resolve it into components, we're going to have this component acting up, right? So this component is basically T sine of theta, right? This will be our angle theta. And we're also going to have this component in that direction, right? Which is going to be T cos of theta. But we have T cos of theta, and this is in equilibrium, the resultant force must be 0, right? So for equilibrium, the resultant force, the resultant force is equal to 0. Number 2, the resultant torque, the resultant torque should also be equivalent to 0, right? So for the resultant force to be 0, if I have a force acting in that direction, I also need another force acting in that direction, right? So if I have a force, right, acting up, the tension cannot be equal to the weight, right? Because I have a weight acting down here, right? It's also going to need a little help from the hinge, right? Because this weight cannot be purely equal to that T sine theta, right? The T sine theta is a resolved component. It's not going to be that big to counteract the weight, right? So there's going to be a little force acting here that will be acting downwards. But remember golden rule, if two forces meet at a point, right, the resultant force will be, or the force acting at that will actually be that over there, right? So the answer will become D, because the force over there will be the force acting in that direction. Very, very important. A diving board of length 5.0, okay, is hinged at one end and supports 2.0 from the end of a spring constant 10,000 kilonewtons. A child of mass 40 kg stands at the far end of the board. What is the extra compression of the spring caused by the child standing at the board? Okay, so the board is going to compress the spring, but the spring is going to exert a force upwards, right? So it doesn't want to be compressed. It's going to say no. It's going to exert a force up, but the body is going to compress it either way, right? The spring is not even that strong. Okay, so this is the force acting upwards on the spring, right? And the child is going to exert a force acting downwards, right? They're about to jump, okay? So we say that this is an anti-clockwise force, right? We say that, that force, right, in regards to this pivot, this force is actually anti-clockwise because we're moving that direction, but this force is actually clockwise, okay, because it's also moving in that direction, right? And I know that my anti-clockwise moments should be equivalent to my clockwise moments, right? My anti-clockwise moments is 40 divided by, okay, so it's 40 times, right? So it's 40. So it's 40 multiplied by 9.81 multiplied by the distance. What's the distance, guys? It's 5.0, right? So the distance is 5.0. Should be equivalent to my clockwise moment is 2.0. Okay, multiplied by my force on the spring, which I don't have and which I need to find, right? So the value of that force F would therefore be equivalent to, multiplied by my force F. Therefore, the value of force F would be equivalent to 40 times 9.81 times 5.0 divided by 2.0, right? So that's going to be 981 newtons, right? But according to Hooke's law, as you can see, according to Hooke's law, we know that F is equivalent to kx, right? So the value of x will be equivalent to the value of F divided by the value of k. So it's going to be 981 divided by 10,000. That's going to be 0.0981 meters, right? So that's going to be about 9.81 centimeters, which is approximately 9.8 centimeters, right? So the answer is C. Very important. Moving to question 14. A granite rock is on the surface of Earth, right? And it has a density rho, right? So we know that density is the mass divided by the volume, okay? And it's transported to the surface of another planet, okay? Another planet. Transported to the surface of another planet, okay? So let's assume that planet is Mars, okay? So it's transported to Mars. So basically Mars is the value of G than the Earth, right? Basically. But the mass is going to stay the same, right? So basically, mass does not change, okay? So mass does not change as place changes, right? Okay, so as place changes, the mass does not change. But, the weight changes, the value of G will also change, right? But the mass will not change. So if mass is equal to density is equal to mass over volume, with the volume change if you're on another planet, it won't, right? Whether you're on Mars or on Earth, your volume is just going to be the same, right? So the density should also remain the same. Okay, very important. Move on to question 15. When we're given a closed U-shaped tube containing a stationary liquid of density rho, one side of the tube contains a gas of pressure P1 and the other side contains a gas of pressure P2 as shown. Okay, so given the acceleration of free fall, which equation is correct, right? So basically, guys, let's consider this point over here, right? Let's consider this point A, right? So we'll divide our beam, rather our manometer, into two different portions, right? The left, okay, and we divide it into the right, right? So considering this point, okay, as our starting point, right? The pressure on the left, since it's in equilibrium, plus, okay, so it's P2 plus, rho times G times the value of X. We no longer have X, okay, so we have this particular height, which is X minus Y minus Z, sorry, so it's here and here, right? So this is X minus Z, right? I hope it's making sense. X minus Z, okay, so that's P2 plus rho GX minus rho gz. Okay, so if you send everything to the same side, is P1, okay, P1, okay, plus rho gx minus rho gx minus P2 is equivalent to rho gy minus rho gx, right? So these two will cancel out, okay? So we're left with P1 minus P2 is actually rho gy minus rho gx, right? Sorry, rho gz, right? So this is z, rho gz over here, okay? So P1 minus P2 will be rho gy minus z, right? And the correct answer is C. So remember, at one point, the pressure will be equal. So the pressure on the left will be equal to the pressure on the right. And the pressure on the left is pressure of the gas plus pressure due to that liquid column that is over there, right? And you should be able to find that correct expression, right? Very important, right? An easier method would just to say at this level, the pressure should be the same. So if this is P1, P1 minus P2 should be equal to rho g. The difference in height will be x, will be y minus z, right? And you just get your value of C. But it's important for you to understand where do these laws come from so that you can be able to apply it on your own, right? Moving to question 16, which product of two quantities is equal to power? Basically, it's force and velocity, right? Because power is basically the work done per unit time, but power is force times distance divided by time. Therefore, power is force times distance over time. Therefore, power is basically force times the velocity, right? So the answer has to be B. Very important. Moving to question 17. Researchers have developed a new type of filament lamp with an efficiency of 40%. What does this mean? It means that power out, okay, of the new filament lamp over power in of the new filament lamp is actually equivalent to 0.4, right? So that's my first equation, okay? And old type filament lamps have an efficiency of 5.0. So power out of old divided by power in of old is actually 0.05, right? That's equation 2. What is the ratio of the power input to one new type of lamp over the input to old type of lamp, right? So basically, power output is essentially 0.4 multiplied by the power input, right? Okay, so that's my equation 3. And then over here, my power output is basically 0.05 multiplied by power input of old, right? So basically, this is power input of old, and this is power input of new, right? So we know that they have produced the same useful power output. So PO is the same. I can equate the two, right? So equating equation, so this is equation 3 and equation 4. Equating equation 3 and 4, right? 0.05 times power in for old will be equivalent to 0.4 times power in for new. My question wanted me to find power in for new over power in for old, right? So power in for new will be 0.05 divided by 0.4 will be equivalent to power in for new divided by power in for old, right? So these two cancel out. I'll be left with a ratio of approximately 0.13, right? So this will be power in for new divided by power in for old. And the answer is A. Very important. A student attempts to derive the formula for kinetic energy. She begins considering an object of mass m, which is initially at rest, right? So basically, let's try to help the student derive the formula, right? So we know that work done is basically force multiplied by the distance, okay? So work done is basically force multiplied by s, okay? So the student considered an object which is initially at rest, right? So v squared is equivalent to u squared plus 2as. So initially at rest, meaning that this is equivalent to 0, right? So for the child, v squared, right, divided by 2a is actually equivalent to their value of s. A constant force F applied on the child, so this is the constant force F that we have, causes it to accelerate to final velocity v, where final velocity v in displacement x. The kinetic energy gained is equal to the work done on the object by the force F. Which equation would the student not need in order to derive the formula? So let's derive it and see what equation we did not use and what equation we obviously used, right? But we know that work done is equivalent to that kinetic energy, right? So the kinetic energy will be equivalent to the force multiplied by, but Vs, this S really, this particular expression is basically going to be substituted over there, right? So basically that's going to be v squared divided by 2a, right? But get this, F is equals to mass times acceleration, right? So the kinetic energy will be equal to mass multiplied by the acceleration multiplied by v squared divided by 2a. Those two cancel out. So EK will be half mv squared. We have derived our equation, right? We had to use this because I said F is equivalent to ma over here, okay? So we basically had to use that equation. W is equals to Fs. Where did you have to use it? We had to use it over here, okay? So this was true. V squared is equals to U squared plus 2s. We had to use it over there, right? But we never used E is equals to half Fs, right? So we never used this equation. So the answer has to be C, right? So number 18, the answer is C. Move on to number 19. We'll be given a wire that obeys Hooke's law and has Young modulus 2.0 times 10 to the power of 11. Okay, the wire has a final length of 1.6 and a diameter of 0.48, right? So how do we work this out? We know that the Young modulus is basically the ratio of stress to strain, right? But stress is force over area. So force divided by area divided by strain is the extension per unit length. That will give me force multiplied by the length divided by, okay, the area multiplied by the extension, right? So basically my Young modulus will be equivalent to my F divided by X multiplied by the L divided by A. But this is actually the value of K. Remember, from Hooke's law, F is equivalent to Kx. So F over X is actually equivalent to K. So the Young modulus is actually equivalent to K times the length divided by the area. So the Young modulus multiplied by the area divided by the length is actually equivalent to the value of K. So if I go here, my Young modulus 2.0 times 10 to the power of 11 multiplied by the area, okay, multiplied by pi, okay, the area of that is pi, okay, d squared length, okay, so all of that divided by my length, which is 1.6. If I punch that on my calculator, that gives me a value of K of basically 2.3 times 10 to the power of 4, which is B. Okay, 20. A wire is stretched beyond by a tensile force, right? Which statement about the elastic limit must be correct, right? The deformation is plastic after the limit has been exceeded, which is true, right? So plastic basically means that if you remove the deforming force, it does not return to its original position. And that is basically the definition of a plastic deformation, right? And it's not until the elastic limit is reached, it is after it has been reached, making B wrong, right? And the extension is proportional to the tensile force after. It's not exactly proportional because it's over, right? Essentially, it's proportional until. Well, the elastic limit can also happen after the limit of proportionality, because the limit of proportionality and the elastic limit are not the same point, right? So that makes C and D wrong. Okay, move on to question 21. Which statement is true for all types of progressive waves? So this is basically straightforward. Progressive waves transfer energy from one point to another. Okay, we'll move on to question 22. Given transverse water wave that is moving along the surface of some water. Okay, this causes a ball to move vertically without moving horizontally as it floats upon the surface. At one instant, the ball is in a position as shown. The wave has a frequency of 0.20 hertz and an amplitude of 0.70. The distance between a trough and an adjacent peak is 2.4 meters. What is the distance traveled by the ball in a time of 20 seconds? Okay, so this is similar to a question that was also asked in regards to motion of projectiles. So the ball is not going to move to this direction, but rather the ball is going to move down, the ball is going to move up, but it's only going to stay in that plane only. Okay, so we just need to find the period, right? So basically I'm given the frequency of 2.20 hertz, 0.20 hertz, right? So my frequency is 0.20 hertz, but I know that frequency is actually 1 over t. Okay, so my t will actually be 1 over 0.20 hertz. So that's going to be seconds, right? So per hertz is going to be seconds, right? So my value of t is actually going to be 5 seconds, right? So my one period is actually going to be 5 seconds, right? So let's count this for the ball, right? So this is the ball, right? And the ball is at its maximum displacement, right? So how does a period work, right? A period will be like this, 5 seconds, that's 1. Okay, if we go down here, that's 2. That's, if we go up there, that's 3. If we go up here, that's 4 motions, right? And all those 4 motions just going to take 5 seconds, right? So we know that the amplitude is 0.70. So those 4 motions are going to take 4, okay, times 0.70, right? But these 5 centimeters, right, we've been told that after a time of 20, how many 5 seconds are in 20 seconds, right? We have 5 seconds in 20 seconds. So it's going to move a total of 4 times. Okay, so basically it's going to move a total of 4 times, right? So if I have this, the displacement for 5 seconds, for 4 times is going to be multiplied by 4, right? And that's going to give me an answer of, I think, approximately that's going to give me an answer of 11.2, which is C. Very important, right? Move on to question 23. A sound wave travels from left to right across a room, okay? So the variations with distance across the room of the displacement of the air molecules at one instant is shown. At which distance will air pressure be the lowest? Okay, so basically, sound travels like this. Sound travels in a series of compressions, okay? So basically sound travels, if it makes a compression, it's then going to make a refraction. Then it's going to make a compression, then it's going to make a refraction, so on and so on and so on. So imagine this. Here, you have a particle moving to the right. So basically, this is to the right, right? But here, you have a particle moving to the left. So you'd agree that this is being squashed, right? Or rather, it is being compressed, right? By particles moving to the right and particles moving to the left, right? But if we were to consider this, right? This particle is actually moving to the right, right? But this particle is actually moving to the left. That makes D a refraction, right? A refraction because the two particles are moving in opposite directions, leaving D as a point of low air pressure. So the answer becomes D. Okay, so very important for you to keep that in mind. A source emits a sound wave of single frequency. The Doppler effect causes a different frequency of sound to be heard by stationary observers. So basically, this is the Doppler effect, which says that relative motion between the source and the frequency results in the Doppler effect. So a source that is moving as it produces the sound wave, it basically has to be true because the source has to be moving, produces a sound wave, and that is going to cause the Doppler effect. Okay. Move on to question 25. An electromagnetic wave is free in space at that frequency. Which region to the electromagnetic spectrum includes this frequency? Okay, so we know that V is equivalent to F lambda. So the value of lambda will actually be 3.0 times 10 to the power of 8 divided by 2.5 times 10 to the power of 14. Okay, and that's going to give us an answer of approximately, okay, that's going to be an answer of approximately 1.2 times 10 to the power of negative 6 meters. That's my wavelength. And the answer is infrared. As you can see from the order, infrared is the one that is between, 400 times 10 to the power of negative 7 to about, 10 to the power of negative 3. So it has, to about, as you can see, infrared is the one between 700. As you can see the range of infrared over there. It could only be infrared that is with a wavelength of 1.2 times 10 to the power of -6. Okay, very important. Moving to question 26. Two polarizing filters are placed next to each other so that their planes are vertical. So let's draw it. So we have this particular line over there, okay? Right. And we're going to place two polarizing filter. And the first polarizing filter has its transmission axis at an angle of 50 degrees to the vertical, okay? So basically, this is going to be the transmission axis of the x vector, and it's going to be at an angle of 50 degrees, right? So it's basically going to be something like that, right? And it's going to be at an angle of 50 degrees. So this is basically, okay, 50 degrees, right? So if you're talking of Malus's law, before we even answer the question, we know that if I have intensity I not coming here, the intensity that will come out here will basically be I is equivalent to I naught cos squared of 50, right? Because it's coming out of that polarizer, right? Very important. Okay, let's extend this. And we've been told that the second polarizing filter has a transmission axis at an angle of 20 degrees to the vertical, right? So it's 20 degrees to the vertical. Okay, so let's go to 20 degrees to the vertical. So we're going to draw the second one. Okay, and the transmission axis is going to be something like that. Okay, so this is going to be 20 degrees. Okay, so this is going to be 20 degrees to the vertical, right? So the angle between the transmission axis of the two polarizing filters is therefore 30 degrees, right? So the angle between this transmission axis and the other transmission axis of that wave is actually going to be 30 degrees. And that is the angle that we're interested in Malus's law. Remember, I always say this, in Malus's law, you have to think of the transmission axis, you have to think of the polarizer, and you have to think of the analyzer. Once you understand that, you're done with Malus's law. So the intensity that's going to come out here is going to be I naught cos squared of 30. What is the I naught is basically this, right? With reference to this particular situation, okay? So if I have light with an intensity of 8.0, so for the first scenario, it's going to be, right? For this scenario, it's going to be 8.0, okay? So for that scenario, it's going to be, okay? So it's going to be 8.0 times cos of 50 squared, right? That's going to give me an answer of about 3.30. That's what the one that I'm going to take here. It's going to be 3.30 times cos of 30, all of that squared. That's going to give me an answer of 2.47905, approximately 2.5 watts per meter squared, right? So basically, if it's going to come with 3.3, 8.8 times cos 50, that is going to be that intensity, which is my initial. The other one is going to have a 30, cos squared of 30 is 3.3 times cos of 30. That's going to be 2.5. So the answer is going to be B, basically. Question 27. A stationary wave is stretched on a stretched spring, okay, and it's set up between 2 points, point P and point T. Which statement about stationary wave is correct? Point R is a node. No. Point R is actually an antinode, right? So point A is wrong. Point Q and S vibrate in phase. That is correct. Whenever we talk of stationary waves, right, if this is an antinode, two antinodes vibrate with a phase difference of 180 degrees. A node, basically, the other one, the antinode in that antinode, vibrate with a phase difference of 360. What does it mean? If Q is moving down, S is also moving down, but R is moving up, because the phase difference between Q and R is 180. They do the opposite of each other. If one moves down, the other moves up. But when Q and S are actually vibrating in phase. The wave do not so B is correct. The wave do not transfer energy, the stationary wave, so they can't transfer energy from one point to another. The distance between P and T is actually 3 wavelengths, or it can't be, because this is a node, that's a wavelength. A node to a node, that's a half a wavelength. So basically it's about 1.5 wavelengths. So it can't be 3 wavelengths. So C is wrong, okay? Moving to question 28. A bar vibrates with a frequency F and it produces water waves in a ripple tank, right? So basically this is the wavelength of, basically the wavelength of the water wave. And this is the value of the gap, right? So gap of width X, okay? So, which combination of vibration of frequency will produce the smallest angle of diffraction? So, how does the smallest angle of diffraction happen? Basically, the smallest angle of diffraction happens when the so get this, the smallest angle of diffraction happens when the gap width is so big, but the vibration is so small, right? So we have three scenarios, basically. The first scenario, if, okay, if the wavelength, right? So basically, if you have something like this, right? Okay. So if the wavelength lambda and the gap x, so if lambda is approximately equal to x, that is where we have the maximum diffraction occurring, right? The maximum diffraction occurring, right? The second scenario, if lambda is greater, right? Lambda is smaller, sorry. If lambda is smaller than x, okay? So if like that, this is the value of x, okay? But this is the value of lambda. This is the value of x, okay? So this is the value of x and this is the value of lambda, right? So basically, if x is way greater than lambda, then we have the smallest angle of diffraction, right? So the smallest angle of diffraction would therefore be present, right? And then the third one, the third scenario, if the gap is way small, okay, so x is way small than the wavelength, right? Basically something like that. So if x is way less than the wavelength, then we have no diffraction occurring, right? It can't even fit through. How do you expect it to even diffract if its wavelength is so big that it can't even fit through the gap? It doesn't make sense, right? So we want the greatest difference between x and lambda for us to have the smallest angle of diffraction, and we want x to be approximately equal to lambda for us to have the greatest diffraction occurring. Okay, so if we look here, we know that v is equals to f lambda, right? So f is inversely proportional to lambda. Okay, so for constant speed, of course. So if I have f over 2 here, it basically means I have 2 lambda, right? So if I halve the frequency, I double the wavelength, right? But here the gap width is x over 2. Get this, the gap is actually x over 2, but the wavelength is actually 2 lambda. That's way big, meaning this scenario actually models situation 3, right? The next one, if I have f over 2, right, which is basically 2 lambda, right? And this is basically 2x, which is also 2x. This is basically, these are approximately equal, right? So I should have a bit of maximum diffraction occurring. So in this scenario, sort of tries to model, okay, this, scenario in the first one, right? Here I have 2f, right? If I have 2f, this will give me half lambda, double the wavelength, double the frequency, half the wavelength, right? So I'm going to have half of lambda, but this is x over 2, right? These are, again, they're almost equal, okay? So these two guys, they're almost equal, and this, again, models, okay, the first scenario, right? But the last one is 2f, right? 2f means I have half of lambda, okay? Half of lambda, right? And this is just 2x, right? And this scenario, okay, models the second scenario, which is over there. That is where I have the smallest angle of diffraction, right? So my answer has to be D, because I've said that the smallest angle of diffraction occurs when the wavelength is so small and the gap is so big, right? And that only happens in D, because that is when we have half a lambda, but we have 2 times the width, the gap, meaning that is going to be the smallest angle of diffraction. So you need to know those 3 situations. If they're approximately equal, you have the maximum diffraction occurring. If x is greater than lambda, you have the smallest amount of diffraction occurring. If x is actually very less than lambda, no diffraction even occurs. The light is not even going to pass through. Very important. Question 29. An outdoor concert. Okay, so very important. Move on to question 29. An outdoor concert has 2 large speakers besides the stage for broadcasting music, okay? In order to test the speakers, they're made to emit sound of the same frequency and the same amplitude. The curved lines represent where is the largest sound heard. So basically, when you have these questions, the loudest sound is heard when we have what we call constructive Okay, constructive interference, right? And constructive interference basically means that the waves meet in phase. The crest of one wave meets the crest of another wave. How this looks is basically it's where the lines form an X, right? That's way of constructive. For example, look at this. I have perfect X's aligning here. That's constructive. I have perfect X's aligning here. That's constructive. I have perfect X and X and X aligning here. That's constructive. They're perfect also here. That's constructive. They're perfect also here. That's constructive. They're perfect also here. That's constructive. Okay, right? So the only scenario where they're perfect, again, is also here. Okay, slightly here, right? That's also perfect, right? But it didn't pass through C. It only passed through D perfectly. So whenever two X's intersect, that is where you're going to hear the loudest sound. So your answer is going to be D. Move on to question 30. In that equation, well, again, I always say this is the diffraction grating. Whenever you see a diffraction grating, one equation must come to mind. D sine theta is actually equivalent to n lambda, where n is the number of the intensity maxima, which is the order of intensity maxima, and D is the distance between adjacent slits in the grating. So the answer is going to be C. I'll move on to question 31. We'll be given the diagram showing a metal block. The block has sides of length A, B, C, okay, as shown, and the volume is V. Each charge carrier has a charge of negative Q, and the number density is N. It takes each charge at an average time of time T to pass through the block. So what is an expression for the current? Okay, so I know that I is equals to NAVQ, okay, very important. But I know that velocity is actually going to be the length that has been moved divided by the time. What is the length that it is moved? It is moved B, because if you're considering this and this is what it has traveled when moving through this block, right? So it's the length of B divided by time of T that it's going to take, right? That's the velocity. But the area is this cross-sectional area, right? This cross-sectional area, which is basically A multiplied by C. Okay, so the current will be N multiplied by A multiplied by C multiplied by B divided by T multiplied by Q. But get this, the volume of this thing is actually the length times the width times the breadth, which is A times B times C. So I can basically substitute this V and let it replace everything that is over here, right? That means I will basically be equivalent to NQV divided by T. NQV divided by T. My answer is B. Very important. Question 32. What is the ratio of power in lamp X and power in lamp Y? So we've been given two lamps X and Y connected to a cell. The current in lamp X is 0.50, resistance is that. The current in lamp Y is 3.0, and the resistance is that. So basically, power is equivalent to VI. So power is I squared R. So power in X will be I squared R divided by power in Y will be also I squared R. So the current here is 0.50 squared multiplied by R, which is 9.6, divided by the current over there, which is 3.0 squared, multiplied by R, which is 1.2. And that's going to give me a ratio of approximately 0.22, okay, 0.22, which is equivalent to A, right? Very important. I'll move on to question 33. The intensity of an LDR is increased. So basically, an LDR, something like that, as you increase the intensity of an LDR, so it's increased the intensity of an LDR, the resistance actually decreases. As you increase the intensity, the resistance actually decreases, right? If we go to a thermistor, okay, so if we go to a thermistor, about the same will also happen, right? For a thermistor, if you increase the temperature, the resistance is basically also going to decrease, right? So for a thermistor, something like that, resistance, that's the temperature, right? If you're going to increase the temperature, okay, the resistance is basically going to decrease, right? So what happens with the potential difference across each component? I know that V is equivalent to IR, okay? So if I'm going to decrease the resistance, I'm also going to decrease the potential difference in both scenarios. So it's going to be decreasing, decreasing in both scenarios. So the answer is going to be D. Very, very, very important for you to be able to think of that. Question 34. We've been given an iron wire that is a length of 8 meters and a diameter of 0.50 millimeters. The wire's resistance R, and the second wire is that length and that diameter. So basically, they're both iron wires, meaning they're made up of the same material. So you need to be looking out at that. So they have the same resistivity. So we want to find the resistance of the second wire. So how do you go on about this? Well, get this. We know that resistance, okay, so let's work it out. We know that resistance is basically equivalent to rho L divided by A, right? But area is actually pi d squared over 4, okay? So we can take this and substitute it over there, okay? So the value for resistance would basically be rho L divided by pi, okay? Pi d squared over 4. So our resistance will basically be 4 rho L divided by pi d squared, right? So this is our governing equation that we're going to be applying, okay? So let's go back to the first iron wire, okay? So the resistance of the first iron wire is going to be 4 multiplied by its resistivity, okay? And we're given the length of that iron wire, okay? So multiply by the resistivity, multiply by the length of that iron wire, which is basically 8.0, okay? So the length is 8.0 divided by pi, its diameter is 0.50, 0.50 times 10 to the power of negative 3 squared, right? So I can find the value of rho, okay? But power is actually v squared divided by r. An increase in the power means that the v loss is also going to increase, and the v terminal is also going to increase, causing the v loss to decrease. If the v loss decreases, the internal resistance will also decrease, right? An increase in the charge carriers leaving the cell per unit time just going to increase the current. So the answer has to be B, because as I decrease my potential difference, my V loss will also increase, hence my internal resistance has to also increase. Very important. Moving to question 36, Kirchhoff's first law and second law. You just have to know this. First law is the conservation of charge, and second law is the conservation of energy. The answer is A. Question 37, very important. So I'm going to be explaining a little bit about potentiometers and how potentiometers actually work. So in this question, we've been given a potentiometer circuit that is used to determine EX of a cell. So we've been told that the circuit contains a second cell of known EMF E0 and negligible internal resistance, right? And we've been told that EX is going to be less than E0. So basically we can assume that E0 is going to be our parent cell. Okay, it's going to be our main cell that we're going to be dealing with, and EX is going to be our small cell, okay, that we're going to be measuring, right? So basically, we can easily say that A is the correct answer because E0 is the parent cell, but B is wrong because EX is not the parent cell, right? And look at C. E0 basically, yes, is the parent cell, correct? And in D, E0 is also the parent cell, right? So we eliminated B, because if E0 is going to be greater than EX, it has to be the parent cell, right? So let's first start with the first scenario, right? This is the positive terminal. This is the negative terminal, meaning at P is going to be positive, at Q is going to be at negative, right? And if you look at here, this is going to be a negative, and this is going to be a positive, right? But as you can see, there's a potential difference over here. This is positive, that is positive, right? So current is actually going to flow in the circuit itself, right? So the galvanometer will not be zero. Remember, with an EMF, with the potentiometer, if the galvanometer is zero, it means that the potential across this point, PJ, is equivalent to the potential across EX, right? But if there is a potential difference, it means that, if they're not connected against each other, it means that I cannot measure my potentiometer. So A is wrong on that regard, because remember, the potentials have to be the same so that no current flows through in the downward circuit. If you look at C, look at where the galvanometer is. How are you even going to measure EX? It doesn't make sense, because EX has to be needs to have the galvanometer close to it so that we can be able to measure the current flowing through the galvanometer. It's not going to happen if EX is actually below and E naught is having the galvanometer itself. What exactly are we trying to measure? Making C wrong. But why exactly is D correct? Get this. If this is negative, it means that this point is going to be negative, right? Because this is negative and this is positive, right? It means that this side is also going to be positive. But look at this. This side is also going to be positive side, and that side is also going to be a negative side. There is no potential difference. They're connected against each other. The negative, positive of that, and the positive of that, the negative that and negative of that are the same. Current can't move through here. Why? Because it's positive, right? It's also positive. That is also positive. So it won't move there, right? And it can't also move in the other direction. Because why? It's negative there and it's also negative, right? So there is nothing that is going to move. No current will move through in this region, provided that PJ, the voltage across PJ, is equivalent to the EX that is there, right? So no current will be able to flow through based on that regard. So the answer is D, because they have to be connected the same. Look at the potential difference, right? The galvanometer is only 0 if no current flows through. Question 38. In an experiment of an alpha scattering particle, alpha particles are directed at a thin gold foil. Most of the alpha particles pass straight through the foil or are deflected by a small angle. Okay, a small number of alpha particles are deflected by a large angle. Which statement cannot be deduced from this experiment? Okay, so the first statement, atoms is made up of mostly empty space. We deduce it from this experiment that most of them pass straight through, meaning the atom is mainly empty space, right? Most of the atom is concentrated in the nucleus. We mainly deduce this from this deflection, that a small number are deflected large angles, meaning they actually go back. The nucleus is small, comparable to size to the atom. We actually deduce that because if it's going to deflect a very small number of particles, it means that it's pretty small, right? But we don't necessarily know that it contains protons, right? We can't tell because we just know it's being deflected. We can't say that from that experiment we know that they're protons. How do you know that they're protons? What if it's something else, right? So we can only tell that the atom is small because it's what we're observing. We're observing that the mass is concentrated because it's bouncing back. We're observing that it's made up of empty space because most of the particles are passing through. We're observing that it's small because very few particles are being deflected. But how do I know that they're protons? How do I know just by observation? I don't. I first need to know that there are protons present. Move on to question 39. We've been given 4 nuclei, which are represented below, and we've been asked to know which statement is correct, right? A charged atom of element Q contains 24 orbital electrons. It doesn't. Q actually contains 13 electrons, so A is wrong. B, nuclei J and M are isotopes of the same element. Isotopes have the same proton number, but different neutron number. G and M have different proton numbers, so B is wrong. C, when E absorbs a neutron, so if E absorbs a neutron, it becomes 29, that is 14E, okay? And emits an alpha particle, minus 4, that's 25, minus 2, that's 12M, it forms particle M. Voila, that's correct. And when M emits a beta minus particle, M transforms into Q. That doesn't make sense because here, look at this, the nucleon number has changed, but a beta particle does not change the nucleon number. So the correct answer is C. Move on to our last question, question 40. A neutron is comprised of 1 up quark and 2 down quarks. When a neutron decays into a proton, a beta particle is emitted. What is the change in the quark composition of a neutron during the emission of beta minus particle? So remember this, beta minus, like I always say, right? Beta minus, this N means that it's a neutron that turns into a proton, right? So it's a down quark that is turned into an up quark, releases a beta negative and an electron antineutrino. And the answer is B. Thank you for watching. I'll see you in the next one. Thank you guys for watching. I hope you like the content. Please subscribe, and if you have any queries or comments, put them in the comment section below. I'll see you in the next one.